All right, let's dive right in. Today, we're taking on a real classic, a rite of passage for many physics students, problem 1.83 from i.e. Irodov's Problems in General Physics. Now, if you know this book, you know its problems can be tough. But this one? It's a fantastic way to learn a problem-solving method that you can use for pretty much anything. So, let's crack this thing open. So here it is, a particle, a circle, and we need to find something called the modulus of the average vector of the force. We've got to do it for two cases, one where the speed is constant and another where it's speeding up from a dead stop. Now, pay close attention to that phrasing, modulus of the average vector. That's not just fancy talk, it's a classic trap, and it's exactly what we're going to pick apart today.
And that's the million-dollar question, isn't it? You stare at a problem like this, you know the formulas for force and momentum are rattling around in your head, but connecting them, it can feel like you're totally lost in the woods. But what if I told you there's a map?
Well, there is. And this is it. This is our plan of attack. We're going to use this roadmap to break this problem down, piece by piece. And the best part is, this isn't just for Irodov 1.83. This is a framework you can use for any tough physics problem that gets thrown your way. You know, the secret to cracking these tough problems, it's not some hidden formula you have to memorize. It's all about having a solid method. And the coolest part is, the author himself, i.e. Irodov, actually tells us how to approach his problems right in the book's preface.
And there it is. That's our guiding principle, straight from the man himself. We're going to use Irodov's own advice to solve his problem. It's not about finding the answer in a textbook. It's about building a way of thinking. First, understand what's really being asked. And second, and this is huge, draw a picture, visualize it. Okay, let's put that advice into action. We're going to deconstruct this problem into its most basic parts, just like taking apart an engine to see how it works. We're not even going to think about equations just yet. First, we need to get a handle on the pieces we have to work with. So, let's take inventory. What's in our toolkit? We've got the mass, m, and the radius of the circle, r. Easy enough. For part A, we know the speed v is constant. For part B, it starts from rest and has a constant tangential acceleration. That just means its speed is picking up at a steady rate as it goes along the curve. Now, for the most important step of all, what is our actual goal? We need to find the modulus of the average vector of the force. Here's what that means, and listen closely. We have to find the average force vector first, and then find its magnitude, its length. This is totally different from finding the magnitude of the force at every point and then averaging that number. That's the trap. Okay, so we've got our knowns, our starting point, and we have our goal, our destination. How do we build the bridge to get from one to the other? We need the right tool, the right physical principle. And when you see the words average force, there's one definition that cuts right through the confusion. This formula right here, this is the master key to the whole problem. The average force vector is just the total change in the momentum vector divided by the time it took for that change to happen. And if you look closely, this is really just a version of Newton's second law, F equals ma, just dressed up in terms of momentum. So our whole job boils down to just two things: find the change in momentum and find the time. Okay, I want you to really lock in on this slide. This is where so many people go wrong. On the left is our hero. That's what we need. You find the momentum vectors at the start and end, subtract them, get the magnitude of that result, and divide by time. On the right, that's the pitfall. That's trying to average the magnitude of the force over the path. It's a way more complicated calculation, and more importantly, it's not what the problem is asking for. All right, with our map laid out, our key principle in hand, and knowing the big trap to avoid, we are ready to go. Let's apply this method to part A, where our particle is cruising along at a constant speed v. Let's walk through this together. Step 1. Let's draw it. Imagine our particle starts at the top of the circle, moving to the right. Its initial momentum, mv, is just mv pointing along the positive x-axis. After a quarter circle, it's at the far right of the circle, moving straight down. So its final momentum, mv, is mv pointing in the negative y direction. Step 2. Now we find the change, delta p, which is p final minus p initial. It's a vector subtraction. Step 3. We need the magnitude of that change vector. Using the Pythagorean theorem, it's just the square root of mv squared plus mv squared. A little algebra, and that gives us mv times the square root of 2. Step 4. How long did it take? Well, the distance is a quarter of a circle, so pi times r divided by 2. Time is just distance over speed, so our time is pi r over 2v. Step 5. Now we just put it all together.
And there it is. We take our change in momentum, mv squared the 2, and divide it by our time, pi r over 2v. When the dust settles, we get this expression. And it makes sense, right? The force depends on mass, the square of the velocity, and the radius. That feels right for something moving in a circle.
Okay, part A is done. Now for part B. The particle starts from rest and speeds up. This might seem harder, but our fundamental principle, average force equals change in momentum over time, is still our guide. It always works. We just need a little help from kinematics this time.
So the steps are pretty similar. Step 1. The particle starts from rest, which means its initial momentum is 0. See? This actually makes our lives easier. The change in momentum is just the final momentum. Step 2. To get the final momentum, we need the final velocity. We can use the good old kinematic equation, Vf squared equals Vi squared plus 2as. Here a is our tangential acceleration and s is our quarter circle distance. We can solve that for Vf. Step 4. We also need the time. We can use another kinematic equation, s equals Vit plus 1/2 at squared, and solve for t. Step 5. Finally, we just divide the momentum we found by the time we found.
And now for the big reveal. This is the coolest part. After all that work with square roots and kinematics for the final momentum and the time, when you divide them, almost everything cancels out, and you're left with this incredibly simple, elegant answer. The modulus of the average force is just the mass times the tangential acceleration. It's beautiful. All the messy geometry just vanished.
So, we did it. We got the answers. But you know, like any good journey, the real treasure isn't just the destination. The formulas we ended up with are not the most important thing we've uncovered today. What we've really found is a powerful mindset.
This is the true takeaway. This is your reusable roadmap. First, really truly understand the goal. Next, draw a picture, visualize it. Then, find that single core physical idea that connects everything. Be on the lookout for those common traps. Then, just execute your plan step by step. And finally, when you get an answer, look at it. Ask yourself if it makes sense. This is how you learn to think like a physicist.
So, look, we didn't just solve one Irodov problem today. We unlocked a repeatable method for breaking down any complex physics problem. So the real question isn't about this problem anymore. It's about the next one. What tough problem that seemed impossible before are you going to solve with this method? Thanks for joining me.